Section 6.6 is on the normal as approximation to binomials. And what that means is we can use the normal distribution to approximate the binomial distribution. And it does a pretty good job on it. But this is used especially more so back when calculating the some of these distributions are a little bit on the more complicated-ish side. So normal as approximation to binomial. This is for probabilities p and q. Q is 1 minus p. And sample size n. If n times p, so the sample size times the probability p, is, well, probability of success p, I should say, is greater than or equal to 5, and the sample size times the probability of failure is greater than or equal to 5, are both satisfied, the probabilities from a binomial probability distribution can be approximated reasonably well by using a normal distribution, having these parameters of the mean equaling to the sample size times the probability of success, and the standard deviation being the square root of the sample size times probability of success times probability of failure. Since the binomial distribution is discrete and the normal distribution is continuous, we use a continuity correction, where a whole number x will be represented by the interval from x minus 0.5 to x plus 0.5. The procedure from using a normal distribution to approximate a binomial distribution, we first check the requirements that n times p is greater than or equal to 5 and n times q is greater than or equal to 5. We calculate the mean as n times p and standard deviation as the square root of n times p times q for the normal distribution. We translate the discrete value x to the interval x minus 0.5 to x plus 0.5, and then graph the normal distribution, shade the appropriate area bounded by x minus 0.5 to x plus 0.5. For example, in one of Mendel's famous hybridization experiments, he expected that among 580 offspring peas, so 580 being a sample size, 25% of them, that'd be the probability of success, would be yellow. But he actually got 152 yellow peas. Assuming that Mendel's rate of 25% is correct, find the probability of getting 152 or more yellow peas by random chance. And is 152 yellow peas significantly high? So we need to check n times p. So 580 times 0.25. We'd get an answer of about, well, I shouldn't say about, of 145. And if p was 0.25, q is 0.75. We're going to do 1 minus 0.25. So n times q is equal to 580 times 0.75. If you do that, you get an answer of about, okay, no, I shouldn't say about, 435. So both of these are greater than 5, so we're fine in both of those regards. We could do this approximation. The mean then would be that 145 from n times p. Standard deviation is the square root of n times p times q. So square root of 580 times 0.25 times 0.75. And it would be helpful if it would all fit on the screen, but of course it does not. Let me just very quickly rewrite that out so it all actually fits on the screen. Just so that it's easier to be read. So standard deviation, square root of n times p times q is the square root of 580 times 0.25 times 0.75. Then from this, toss that into the calculator, we would get an answer of about 10.4283. So we want to determine if the probability that x is greater than 152. And that's a very bad 5 on my part. So this will be 152. So this is the same thing as, by using the normal distribution as an approximation, we want the probability that x is greater than 151.5. It's the same thing as 1 minus probability of x less than 151.5. So if we using that normal distribution, then we get 1 minus 0.7324, and this gives us a value of 0.2676. But this continuity correction is used when the normal distribution approximates the binomial distribution. It's made to a discrete whole number x in the binomial distribution by representing the discrete whole number x by the interval from x minus 0.5 to x plus 0.5, which is the same thing that we just did in this last example by indicating for 152, at least 152 is to the right of 151.5. More than 152 will be to the right of 152.5. At most 152 is to the left of 152.5. And fewer than 152 is to the left of 151.5. Exactly 152 is between 151.5 and 152.5. Again, based upon this normal approximation. And based on the same idea from example 1, let's find the probability of exactly 152 yellow peas among the 580 offspring peas. And then, is this information useful for determining that 152 peas is significantly high? So we want the probability of exactly 152. So as we saw from example 1, the mean was 145, standard deviation was 10.4283. Both of those are from example 1. So for this, we are doing for the normal approximation, we're finding the probability of being between 151.5 and 152.5. That's the same thing as the probability of x being less than 152.5 minus probability of x being less than 151.5. And it refers to this spot. So this had a mean of 145. 152 would be about here-ish. So we have 151.5 and then 152.5. We want this tiny little area here. So, tossing this into the normal distribution, we will get 0.7642 for the area less than 152.5, minus the area less than 151.5 is 0.7324. Subtracting these two values, we get 0.0318. Thank you.